Alright guys, let's take a look at today's lesson. Today we're going to be looking at optimization. We'll spend 2 days on it. This is our first day. First thing that I want to talk about is how do we tell the difference between optimization problems and related rates problems, because optimization problems are word problems just like related rates problems are. And so an optimization problem, its identifying factor is that we are asked to maximize or minimize something. We are asked to maximize or minimize something. And we don't have any rates. Like, it's not going to talk about the rate of this or finding the rate of that. We do not, take the derivative with respect to t. This is a completely different type of problem. And so I want you to be able to tell them apart. When you see a word problem, because they're going to be all mixed together. When you see a word problem, to determine what kind it is, you need to look to see if you're supposed to maximize or minimize something, and if it has rates in it. These problems will not have a bunch of rates in them. Okay? So that's how you can tell the difference. The way we do an optimization problem, the setup is kind of similar to what we would do with related rates. These first three are our setup. And it's just a typical word problem setup where we read the problem, we look at what's given, and this is the key right here. What are we going to be optimizing? That should be the focus of your entire problem, is what are we going to be optimizing? Because it's very likely that they may give you, let's say, information about volume and area, and they want you to maximize volume. What that should tell you is, if you have information on two concepts like volume and area, and they want you to maximize volume, what do you think all the area stuff is going to be used for? To substitute into the volume equation, right? So it tells you how to focus. It tells you which equation is the most important. Once we discover that, we go ahead and draw or label our picture. If we're doing volume, we draw a diagram like we did in related rates. We label the variables, the same kind of setup that we did on related rates. Step 4 is writing an equation. So the equation that we're going to write is for what we want to maximize or minimize. Okay, that's what our focus. Now, we may have to write other equations in addition to it. Like I said, if you're given volume information and area information, and the volume is what you're maximizing, you're probably going to need an area equation, maybe solve for radius or something. There will be different things that you would do, but we want to be sure that we focus on what we want to maximize or minimize. That's what we're going to take the derivative of. Once we get that all settled, we get all of our variables where we want them, we get all the information in, we're going to take the derivative of the equation that we're going to maximize or minimize. Now, once we take the derivative, we're going to do the things that we've been learning for several days. We're going to test the critical points, we're going to find them and test them, and we're going to test the endpoints. Now, do we remember what testing the endpoints takes us out of relative mins and maxes, right? And puts us into absolute. We're looking for an absolute. Now, it's not going to always happen where you have endpoints to test. You're not always going to have them, but when you do, you need to test them. Does that make sense? Because some students, like the first one that we're going to do today, does not have any endpoints. I don't want you to think that that is going to happen all the time. Probably about half the time you have endpoints, and about the other half the time you don't. And we're going to do problems both ways, with both types, so you can see them. So if you have endpoints or domain, you have a definite beginning and ending of your domain, you've got to do the candidates test, and you have to test those endpoints as well, not just the critical numbers. Okay? So that is the overall concept that we're going to be working on. We set up the problem, we write an equation for what we're maximizing, we take the derivative, set it equal to 0, do a sign chart, and get our maxes and mins. That's pretty much the process. Okay, and if we have endpoints, we do test the endpoints like we would on the candidates test. So that's the procedure. So we're going to work one problem today, and then we'll do daily work. And then on Friday, we will have day 2 of optimization, and we'll work one additional problem, just like we did with related rates, where I would work one with you, and then we would practice all those problems. Okay, so that's our schedule. Questions? Okay, let's do the one problem that we're going to be working on today together. So here we are asked to find the point on the parabola that's closest to the point. Okay, so let's start out by drawing a diagram, and I'm just going to estimate it. Let's think about what this graph would look like. Remember when the y is squared, it's sideways. Remember that when the x is squared, it's up or down. So this one has a positive a, so we'd be going, something like that. Okay, it doesn't have to be perfect. I'm just trying to get an idea of what I'm being asked to do. I have 0.14. I'm just going to go with it being here. And now, really, the labeling isn't that intense on this problem. We can label the point. There's really not much else. We could label the equation. But as far as setup goes, this one has a pretty light setup. There really isn't a geometric figure to draw. There's no, volume formulas to write down. It's a pretty light setup. We just kind of graph what's going on and label. So that's really steps 1 through 3. Now we're on step 4. And step 4 asks us to come up with an equation that will take care of this. We want the closest. What does that mean? We want to minimize. We want to minimize, and what is it that we're trying to minimize? The distance. We want to minimize distance. That's what we want to do, minimize distance. And so what we've got to do is come up with, how do we do that? How do we measure the distance from a point to an equation? What's one way to do that? The distance formula. So we would use the distance formula here to do our setup. That's the formula that's going to help us determine what the minimum distance is. So we would write our distance formula out. And if you remember, you subtract the x's and square them, subtract the y's and square them. That's our distance formula. Now, it would be to our benefit not to have 2 different variables, just have one, because our work will be easier. We need to decide what we'll do. Certainly this point right here, I went ahead and put as x1, y1. Okay, I put that point in there. I don't want an x and a y. What are my options? What could I do? Yep, take the equation that I'm given, right, and just decide, do I want to solve for x or do I want to solve for y? And basically you would want to do what would be easier computationally. For me, I would rather solve for x, right? Because if I solve for y, I'm going to be dealing with radicals, and I really, although it sounds kind of fun to have a radical inside of a radical and mess with that, I don't know that I really want to do that this morning. So I probably would solve for x. That's what I would probably do. So let's do that. Let's go with that premise. We're going to solve for x. And now, instead of this x, I'm going to put this there instead so that I can have all numbers and y's. So let's go ahead and sub into our formula. So instead of that x, I'm going to put 1/2 y squared. And our x1 was 1 plus. And then that y, I'm happy with that y staying there. And our y1 was 4. Okay, so that's our original setup. So you could go ahead and jump into the derivative there. I really wouldn't. I would prefer to combine like terms, FOIL and combine like terms, because that would be like, it would be a chain with 2 chains inside, and then you're still going to have to set it equal to 0. So I would simplify first. You can, if you want to jump in here, you certainly may. I'm going to simplify first, and when I do that, I'm going to basically just FOIL all that out, and when I do that, I get this. So 1/4 y to the 4th minus 1/2 y squared minus 1/2 y squared plus 1. That's my first piece. And then plus y squared minus 8y plus 16. Okay, so I go through the process of combining like terms, printing it up so that my derivative work is easier. And I have 1/4 y to the 4th. Then minus 8y plus 17. Okay, so now what I've done is I have an equation that is going to, if when I work with it, take the derivative of it, my hope is that it's going to show me the minimum value or the minimum distance. We want to know, find the point, we want to find the point on the parabola that is closest to that point. We want to find the closest point. All right, so now what would we do to minimize or maximize something? We've been working on that for many days now, haven't we? We would take the derivative, set it equal to 0, do all that stuff. So that's what we're going to do here. So let's take the derivative. So we got to do, bring the half down, copy paste the inside, subtract 1, then do the derivative of the inside. And the derivative of the inside is y cubed minus 8. So that's really nice, but I would like it in a form where I can kind of, solve it, set it equal to 0. So I'm going to go ahead and leave the y cubed minus 8 stays in the numerator, and then we'll just turn that into 2 times the square root of this little guy. Okay. So there's always a balance here that we need to talk about between calculator use and not calculator use, because on the AP test, using your max and min finder is not one of the allowable things. They don't set the AP test up so that that is a benefit to you, right? So if you're going to be finding maxes and mins, they're probably going to make you do it on the non-calc part, unless it's so, unless there's another reason behind it. So the issue is, if I give you a calculator on an assessment, you have to go through the calculus part. You have to do all of this. So you would have to find the equation, find the derivative, do the sign chart. That's where it's going to be the bulk of your points, should I give you a calculator, just so that you're aware. I don't want you to think that, in pre-cal what we would do is come up with an equation, stick it in the calculator, and we were, got our answer. That's not what's going to happen here. Certainly the calculator is useful in determining values of weird things like this. How are we going to determine whether I can get a 0 down here or not? It would be to our benefit to be able, and that is an allowable use on the AP test. You are allowed to graph. They encourage graphing on the AP test and using the values. That's okay. It's just they don't advocate a max min finder, because that really doesn't have anything to do with calculus. So in this particular case, this denominator does not yield any zeros or undefines. Okay, so there is nowhere this is 0. And you can tell with your calculator if you want to. If you want to do it algebraically, you can. On one that has something like this, you would have a calculator available to test stuff like that. Okay, not that your work would look different than my work is going to be, but you would have a calculator to test that. Does that make sense? Because I don't want us to take time trying to figure something this complicated out when we have other things that we should be working on. So, just so that we're clear, calculator use is very likely to happen on problems like this. It's just we need to be sure we follow all the steps through, because every step is going to be a point, including the answer. So when we have our derivative, we find our undefines, and there aren't any. We find the zeros. This certainly is factorable, but probably, and I'm sure you have factored many sums and difference of cubes, and I have too, a lot. And I'm pretty sure the second piece never factors, and it's really not going to give us very much, right? I mean, we could factor it and do that, but for this purposes, for this reality we're working on trying to find a max or min, that piece isn't going to be as important. So in this particular case, we can just set it equal to 0 and solve. If we set the numerator equal to 0, we're going to get that y is 2. So, and our question with this is, do we have endpoints? Do we need to do the candidates test? We don't really have any endpoints of our domain, do we? Technically, 0 is the smallest the x value could be, but is that really going to apply to what we're working on? It's really not. We really aren't going to do the candidates test on this one. This just falls in the half of them where you don't need the candidates test. There's another half where you will, but this is one where you won't need to test endpoints. It would, but there isn't anywhere that it turns it imaginary. So, well, there's nowhere where it's 0. And if you want to check the domain, you certainly could. You could graph this whole thing and see. That wouldn't be something I would advocate doing by hand, but you could. And with use of a calculator, you could certainly check that and see if what's going on. Does this impact, our domain? And I don't think it does, but we could check that with the calculator. All right, so we're going to, now we just have relative extrema to check. We really don't have our endpoints. This particular type of a problem doesn't yield that. So when we check, and again, the sign of this, provided it's in the domain, is going to be positive. Right, the 2 is positive, so that's going to yield positive. We just need to deal with the numerator, and our signs would look like this. So it's what we hoped. That is a minimum. And something that was confusing students earlier is I need the point. What point? What point is closest to this point? And so what does this represent? Which part of the point does this represent? It's the y value. Some students are getting really confused and just assuming it was the x value. But we want to make sure we're clear what we have here. So we've got the 2. That's our y value. In order to find the other part of the point, where are we going to have to go? To the original. We have to plug the 2 into the original for y, and then work that out, and we actually just by chance get 2 as well. And so this is our point that minimizes the distance. This is this minimize. Okay, now watch me spell minimize the distance. Or you could say minimum distance at any rate. And that is our first optimization problem. Not with it. No, we're fine. All this work is our justification. Okay, are we okay? Yes? All right.